Hey guys, it's your guy in a room, and I'm here to show you how to do CS50 Project 2.2 PageRank, and I'm going to show you how it plays out. Not going to go too far into the theory, but I will provide a little bit of clarity. So let's go. Let me get rid of myself here. I've downloaded the project right here. I'm going to unzip it, drag it to my desktop, and I'm using VS Code. You can use whatever you want. I'll briefly go through some setup instructions for VS Code. The important thing to note is to run this, you need a corpus as an argument. So what I'm going to do is just say run using launch.json. And this is going to crash, but create the launch.json file. So I just need to add to this a current working directory and have that the workspace folder, and then args, and I'm going to use corpus 0. Then what I want to do is just print this corpus to make sure it's loading. Print corpus. And I can see it printed out down here. You got to get there to start out where you can run it with a corpus as an argument. So this is what our corpus looks like once we have it loaded into Python. It is a dictionary where the keys are things like 1.html, 2.html, and for each one of these keys, there is a set of pages that they link to. So for example, 2.html links to 1.html and 3.html. Okay, so let's start with our transition model. And I've built a Miro diagram that explains this a little bit easier. So if we don't have any links like this unlinked.html, we're just going to have an equal chance to navigate to any one of the pages in the corpus. If we do have links, then we're going to smear these two together. The odds of going to any page in the corpus with a weight of 1 minus d, and then the odds of going to any one of the links with the weight of d. And these are generally going to be much more highly weighted. Okay, so let's code it out. Follow me and do exactly what you see. Let's scroll down to transition model. I'm going to get rid of this exception that we're raising, and I want all of the pages. So I'm going to say all pages equals a list of corpus.keys, and then the number of all the pages, num pages, equals the length of all pages. We're returning a dictionary, so I'm going to say result equals an empty dictionary, and at the end of it all, we will return result. So there's two cases to consider where we do or do not have links. So links are going to be what's in the corpus for the key page. So links equals corpus page. So, and if links, meaning links is not none, we're going to smear those two things together. So we want to navigate to any random page with a weight of 1 minus D, and then to navigate to a link with a weight of D, else, meaning we have no links, we want to navigate to any random page with a weight of 1. So let's fill it in. This one's probably the easiest, so let's do it first. So I'm just going to say we can't say page because we have that variable already. So I'm going to do for underscore page in all pages, result for page equals 1 divided by num pages. For our other condition, we can reuse this same loop and change it a tiny bit. For the top one here, instead of 1.0 divided by number of pages, this is going to be 1 minus damping factor. Now we want to smear that with our probability of navigating to one of our links with the greater weight of damping factor. So I'm just going to say num links equals the length of links, and then for link in links, result for said link plus equals damping factor divided by num links. And that's pretty much it. That will be our transition model. Okay, next let's do our random surfer model, where we start on a random page and then do sample count navigations to other page and just count the number of times we went to each page. So I'm going to go to sample PageRank and get rid of this exception. And I'll just do the same thing, get the list of all the pages. So all pages equals a list of corpus.keys. And then num pages equals the length of all pages. And we're going to start on a random page. So we can say page equals random.choice all pages. And here you want to make sure you have random. So this is importing random. Then n is our number of samples. So for don't care in range of n, we are going to get our transition model. So let's just say our model, and I'm going to do underscore transition model equals transition model of corpus and page and damping factor. Then this is a dictionary, and we're going to use the Python native random. So we just need the weights from it. So I'm just going to say just the weights from each page. So then weights equals, and I'll use some slick Python syntax here, underscore transition model page for page in all pages. So it's just a list of that second value from our page to probability transition model. And then we navigate to the page. So pick a new random page. So then the page equals random.choices from all pages using those weights. And this is going to be a list, so we just want the first item of that list. This is now our random surfer. Cool. So now we just want to make sure that we return a dictionary where the keys are page names and values are their estimated page rank. And to do that, we're going to keep track of how many times we visit each page. And I'm going to call this visits. So visits equals dictionary with page, and I'm going to start them all at 0 for page in all pages. Then real simple, every time we visit, I'm just going to say visit the page. So visits of page plus equals 1. And then we can just divide those visits by n, and that is our page rank. So I'm just going to say return dictionary page visits page divided by n for page in all pages. Now I should be able to run the program and see the result from our random surfer model. Groovy. Okay, so that was kinda hot. How about red freaking hot? How about we do the iterative algorithm? And let's not get scared by this formula just yet. We'll break it down. It's a lot easier than it looks. And if we scroll down to the instructions, they give us a very important clue. The function should begin by assigning each page a rank of 1 divided by n, where n is the total number of pages in the corpus. So let's do that. I'm just going to scroll down to iterate PageRank, and again, kill the exception, get rid of it, get it gone, it's gone, gone good. All right, same thing, all pages equals a list of our corpus.keys, and then our n num pages equals the length of all pages. And I'm just going to put a comment that that's n. So doing exactly what it said, we start each PageRank as 1 divided by n. So PageRanks equals a dictionary for page and 1 divided by num pages for page in all pages. And at the end of it all, let's return PageRanks. That's the first step. Now the iteration step. Okay, now let's look at the iteration formula again. So this is essentially something we keep repeating. So we repeat this as many times as we want, and it should get us closer and closer to the answer. A PageRank of P equals to 1 minus damping factor divided by n plus some junk. Let's forget it for now. Just PageRank of P equals 1 minus damping factor divided by n a bunch of times. So we want to keep doing this iteratively, so looping. Let's do that. So I want to break it down and make it a separate function, each iteration of it. So I'm just going to copy this, iterate PageRank, and make it iterate PageRank iteration. And this is kind of the updated PageRank. So, well, first of all, I want all pages again. So all pages equals a list of corpus dot keys, and num pages equals the length of all pages. And now updated ranks equals a dictionary of page to 1 minus damping factor divided by num pages for page in all pages. And then return updated ranks. That's kind of the left-hand side of the formula. So what we want to do is iterate, so just a bunch of loops. And for now, I'll just do for don't care in range of, for example, 1,000. PageRanks equals iterate PageRank iteration, corpus, and damping factor. And this is going to keep smudging our PageRanks closer to that holy grail. Okay. So let's go even deeper now. Looking at this right side, PRI is the PageRank. So the PageRank that we already have. This is a bit tricky because it's kind of defining itself by itself. And right now, we don't have that in our iterative formula. So let's notice this important clue and use that to modify our function signature. So what we really need here is also like the previous PageRanks. So I'm just going to call that previous ranks. And when we iterate, the previous ranks are just going to be PageRanks. So looking at this formula again, this is a little bit misleading, but this really kind of means for all pages. So I is a page, and we're just saying for all pages, add to the page rank its current page rank divided by the number of links. And then we also have to note that a page that has no links at all should be interpreted as having one link for every page in the corpus, including itself. So let's go ahead and bang that out. So it's all pages. So for page in all pages, and I want to get the links for it, which may or may not exist. So similar to in our random surfer, links equals corpus of page. So that's all of that page's links. And then if links something else, something else. And this really, I'm just going to call it the contribution from each page per the formula. So I'm just going to call it contribution equals the damping factor times previous ranks for the page divided by num pages. And then for underscore page in all pages, we add that to the updated ranks. So updated ranks for that page plus equals contribution. Okay, then for the other half, I just want to get the num of links. Num links equals the length of links. And I've got my handy dandy comment, contribution from each link per the formula. As I said, I'm not going to derive it. Contribution equals damping factor times previous ranks for said page divided by num links. And then we want to add that to each one of the links. So for link in links, updated ranks for said link plus equals this contribution. Quite tricky, but now let's run it. And what we can see is we essentially have the correct answer, or very close. We didn't do everything yet, but this is essentially just doing 1,000 iterations of it and plugging and chugging that formula. So it works. Now let's go ahead and nail it down to the ground. Behold the Emperor of Slime sitting on his throne of slime. So what we've done passes the assignment, but we're not doing it all correct. So this line, the process should repeat until no page rank value changes by more than 0.001. And I've noodled around with this a little bit and decided that perhaps the helper function makes this easy. So let's make that little helper function follow me exactly. Type in all these exact things verbatim. Def greatest difference between ranks A and ranks B. And this is going to be a really simple little function. This is just going to tell us these are two dictionaries, two PageRank dictionaries, and we just want to see what the max spread is between any of these two. So let's do it. So let's start the result at 0 and then loop through them all. We could even do the classic all pages equals a list of, but right here it's going to be ranks A dot keys. And then for page in all pages, result equals a max of result and the absolute value of ranks A for page minus ranks B for page. And at the end of it all, we will return said result. I'll just compress this. I don't feel that a comment is necessary. So now let's just apply that. Instead of constantly updating our page ranks here, let's just call this updated ranks. Updated ranks equals that iteration, and then we'll say the difference equals the greatest difference between page ranks and updated ranks. And then we'll go ahead and update the ranks right now. So page ranks equals updated ranks. And then if difference is less than 0.001, we will break. But we're not doing a loop up to 1,000. We're just going to do an infinite loop. So while true. And if we run it again, we essentially get the same answer again. I believe that's it. If you have any questions, you can shoot them my way, and I might get back to you. Oh.